Hi everybody. On our last lecture, number 25, we began studying chapter 6. And I was working through problem number 645 using the method of joints. So today I am going to actually finish chapter 6. So for chapter 6 we will only have 2 lectures. And I am going to continue this discussion to talk about something called the method of sections. Now, 645 is technically a problem that could be solved either way, and most problems are solvable either way, but one way of doing it is often easier than the other. So what I'm going to do today is finish problem 645 using the method of joints. So I'm taking up exactly where we left off on lecture 25. And then I'm going to talk about the method of sections and solve a problem using method of sections. So for your homework for this chapter, you're going to have only about 4 to 5 homework problems, and they will be indicative of what you could expect for chapter 6 on the final exam. So let's get started. Coming over here to the document cam, you'll see where we left off with problem 645. And in the textbook, problem 645 asks us to find the force in members BD and CD. And so using the method of joints, I'm working through, and I go to each joint, and I've looked at analysis of joint A and joints. I guess I just looked at analysis of joint A. And what I found so far is that the force in member AB is 36 kilopounds in compression, and AC is 45 kilopounds in tension. So what I want to do next is to move over and look at member CD, which is, or BD, which is what was asked from the problem, and CD. So in order to get the force on BD, I'm going to look at joint B. All right. So we know that AB is 36 kips in compression, meaning that it's pushing on the joint. So what I want to show you is that when we look at, force AB. When we looked at AB at joint A, it's pushing on the joint, so it's moving to the left. Here at joint B, it's pushing to the right because it's still pushing on the joint. So the point that I want to make here is that the direction of a force in a structural member changes from one side to the other because it's not the same criteria that we've used before where something is positive to the right and negative to the left if it's in the x direction. But in this case, it's either going to be pushing on the joint or pulling on the joint. So we need to take that information and bring it over to the next joint. So having said that, we know that AB is pushing on the joint and has a magnitude of 36 kips. When we do a summation of forces in the x direction, let's say x, sorry, that means that the only 2 forces going into joint B are AB and BD. And if AB now we look at pushing to the right, BD has to be pushing to the left with the same amount, or 36 kips. That also means that it's pushing on the joint and therefore is in compression again. Now, this structural member, BC, is purely y direction, and what that tells us is there's nothing to oppose it, so we know that the summation of forces in y direction have to be equal to 0. That means BC is also equal to 0, or BC is a neutral or non-bearing member in this loading scenario. All right, so now we have identified one of the answers for this problem, that BD is equal to 36 kips, and it is in compression. The next piece of information that we need is what's going on here in CD. And as you can tell, that can be a more complicated problem. If we came up here to point D, we would have this, we would not have this, we would not have this, we would not have this, and we would not have this. So in other words, going into joint B, we have 1, 2, 3, 4, 5 structural members, and we only have 2 equations, summation x, summation y. So we can't solve coming here to point D. But if we come here to point C, we already know AB from our first joint. We know that this is neutral. We don't know this, but we know this. And we need to know this, pardon me. So this is known, this is known. We have 2 unknowns and 2 equations. So we need to do our next point of analysis at C rather than D if we're going to stay with the method of joints, which is the only method we know right now. So we're going to look here at point C, and we're going to view everything going into point C as being a force. So we have AC operating right here. We have BC operating right here, which we know is 0. We have CD operating like this, and we have CE like this. All right, so if we go back to our original analysis on point A, we see that AC is 45 kilopounds, and it's in tension, meaning that it is pulling on the joint. So here it's going down, here it's going up, because it's pulling on joint C the same as it was pulling on joint A. We know that this is 0, so we can actually eliminate that from our analysis, can't we? All right, now to determine the direction of these two, what we can tell is each one of these has a horizontal component, but only this has a vertical component. Okay, so that means if this one's going up, this one's going to have to be going down. And if this one is going down and this one is going up, you'll see they're both going to the left, so that means that has to go to the right. So we can do that piece of analysis before we even get started with the problem. All right, now, since we know the magnitude of AC, which is 45 kips, we can then go back and do summation forces X equals 0, summation forces Y equals 0, and we can find out what the tension, in this case we're pushing on the joint, so it's not tension, it's compression in CD. We can determine that value using these equations. All right, so what do we have in the X direction? Well, we have negative AC in the X direction minus CD in the X direction plus the whole entirety of CE, because it's all horizontal, all in the X direction, equals 0. And in the Y direction, we have positive AC in the Y direction minus CD in the Y direction. Those two things added together equals 0. This is going to be easier for us for 2 reasons. One is because there's only 2 unknowns, and this is the one we want. The other is that we have the magnitude of AC. All right, now we need to go back and do a little bit of trig, because the component of those 2 things in the Y direction are going to depend upon the dimensions of this truss. So AC, if we draw this little triangle right here, A to C, the distance from here to here, the horizontal distance, is 10 feet. And the distance from here to here is 7.5 feet. Similarly, the distance from here to here is 10 feet, and the distance from here to here is 7.5 feet. So one thing you may see is that there's a lot of symmetry there, but we're just going to go ahead and work out the math anyway. All right, so I'm going to do this a little bit, not a shortcut, but a little bit different way. It's the same idea, but let's look at this structural member. If this is 10 and this is 7.5, this angle, theta, is equal to the inverse tangent of the opposite over the adjacent. The tangent to minus 1 of 7.5 over 10. And I think I found this in the last problem, but we'll go ahead and do that. So if we take 7.5 divided by 10, we get that that's 0.75, and if we take the inverse tangent to that, we find that that angle right there is 36.87 degrees. All right, so in the y direction, y is opposite, so this is going to be AC, which we found has a value of 45 kips, times the sine, because it's opposite, of 36.87 degrees, minus CD, which is what we're looking for. And now if we look at our triangle for CD, the component in the y direction, if we look at, let's say, this angle, we're going to say that the tangent of this angle is going to be the opposite over the adjacent. So in other words, this angle is exactly the same as this angle. We could have done that using alternating interiors, or we could have said this is parallel to this and so forth. Same idea. So this is going to be same angle. So this is going to be the sine of 36.87 degrees as well, equals 0. And so those cancel out, and we get 45 kips is equal to CD. All right, so the second piece of information is that CD, this is the last piece that was asked for in this puzzle, is 45 kips. Only by looking back at our diagram, we see that CD, I'm looking at BD here, just a second. All right. This is AC, and it's pulling on the joint. This is CD, and it's pushing on the joint. So that means this is also in compression. All right, so this outlines how you do the method of joints. One thing that I want to point out to you here when we start talking about the method of sections is the further you get into a truss, the harder it's going to be to use the method of joints. The reason is you generally have to chase it back from a reaction or a point of connection where you have some known information. And if you get down here into the middle of a truss, it can be quite difficult, or it can be quite time consuming. So we have another method, which is called the method of sections. This is the last thing that we'll study in Chapter 6. And the method of sections uses the same idea that the summation of forces in the x direction is equal to 0, summation of forces in the y direction is equal to 0, and that the summation of moments about any point on the truss has to be equal to 0. But what the method of sections allows us to do is to just look at a part of a truss. In other words, if we have a truss and we cut it in the middle, and we look at the forces that have been cut, or the structural members that have been cut as being forces, we can say that that piece of the truss also has to obey these rules. But after we cut the truss, it also means that we have a shape. So we're not just going to be able to sum forces, we're going to be able to sum moments as well. And what this allows us to do is to get to a specific structural member very, very quickly. So I'm going to look at problem. I'm going to take a look at section, or problem number 51, 6.51, where it asks us to find the force in DE and the force in DF. Now, in order to do this, we have some geometry. I'm going to go ahead and draw the truss, and then we're going to talk a little bit about using the method of sections in order to not have to chase the analysis through each one of the structural members. Okay, so 651. We have this truss, which I will draw. This is like a roof truss, isn't it? It's pointy. It's all triangular, of course, but it's also a little different geometry than the one we just used. Okay, and we have a rolling connector here at K, which means that we could have a vertical reaction at K, but not a horizontal reaction. And then over here at point C, we have a fixed support. So we could have a reaction at C in the y direction, but we could also have a reaction at C in the x direction. Now, I can see that it's going to be equal to 0 because there's nothing to oppose it. So in other words, none of these applied forces are in the x direction. So that means that since the summation of forces in the x direction have to be 0, and r sub cx is the only x directional force, it has to be equal to 0 because there's nothing to oppose it. Summation of RCX equals 0, therefore RCX equals 0. All right, we are told that the entirety of this truss from end to peak has a height of 7.5 feet. So that's going to give us some information about our geometry, about our trig. And we're told that each of these panels is 6 feet long. Okay, so there's 6 of them. The whole thing is 36 feet. And the next thing is we need to label all of our points and finish drawing the truss. So we have A, B, D, and F going up. And then we have H, J, and L going down. Here at point C, we have another structural member from C to D. Here at point E, we have a structural member going from D to F. Here from F down to point I, we have a structural member that looks like this. And from H to K, we have a structural member that looks like this. All right? And what we want in this problem, 651, determine the forces in members DE and DF. All right, so the first thing we need to do, we have some applied forces at point A. We have P, it tells us that it's 20 kips. At E, 20 kips. At G, 20 kips. At I, 20 kips. And at L, 20 kips. All right, so just like with method of joints, the first thing that we need to do is to do statics of our entire truss. We need to say the summation of forces in the x direction equals 0, summation of forces in the y direction equals 0 for the entirety of the truss, and that the summation of moments about any point on the truss have to equal 0. We're doing that to find our reactions at C and K. Okay, first of all, in the x direction, we get reaction C at the x direction equals 0, so that one's easy. In the y direction, we have pointing upward, pushing upward, r sub c in the y direction, and r sub k in the y direction. And in the negative y direction, we have 20, 40, 60, 80, 100. So I'm just adding all those 20, let's just say 5 times 20 kips equals 0. So I know that r sub cy plus r sub ky equals 100 kips. But I don't know how much of that 100 kips is here is reacted here at C and how much is reacted at K. So in order to find that out, I'm going to take moments about some point, and I could choose either C or K to take my moments about, but I'll choose C for no particular reason. But I'm going to say the moments about C, I could have just as easily chosen K, but I want to choose C or K because that will eliminate one of those variables from the equation. I'll be able to solve directly now for r sub K in the y direction and then plug it into this equation to find r sub cy. All right, so pretending like I've got a pin here at C, this 20-pound kip, or this 20-pound force at A, is acting 6 feet away, and the rotation is counterclockwise, so that's positive. This 20-pound kip, or 20-pound force, is also, 20 kip force is acting 6 feet away, but its direction is clockwise, therefore negative. This 20 pounds, 20 kips, is acting 12 feet away. It's clockwise, so it's negative. This 20-pound kip, this 20 kip force is acting 18 feet away, also negative. Now R sub k, if I think about pinning it here, R sub k in the y direction, which is acting at 1, 2, 3, 4, 6 times 4, or 24 feet from point A, is going to induce a counterclockwise moment, so that will be positive. And then last but not least, we have this negative moment from the 20 kip force that is 30 feet away, and all those things add together to be 0. So you can see from this equation, I can solve immediately for R sub k in the y direction. R sub k in the y direction is equal to, I'm going to take the ones that are negative over here will be positive on the right-hand side. So I can factor the 20 out and say 20 times 6 plus 12 plus 18 plus 30, right? Because 20 times 6, 20 times 12, 20 times 18, 20 times 30, and then I have to subtract this one off, minus 20 times 6. And then since this is multiplied by 24, I take this entire thing and I divide it by 24, and I can solve directly for R sub k in the y direction. So I can once again combine 20s together here, and I have 6 minus 6. Those two go away. And so on the top, I just have 20 times 12 plus 18 plus 30. 12 plus 18 is 30, plus 30 more is 60. Divide that by 24. And the value of R sub ky then is 20 times 60 divided by 24, and that value is 50 kips. All right, well, if R sub ky is 50 kips, that must mean, if you look at that, R sub cy has to be 50 kips as well, so that they add to 100 kips. So I have R sub cy is equal to 50 kips, and R sub ky is also equal to 50 kips. All right, so we're on pretty familiar territory up till now. And now we're just going to go a little bit broad and do this thing that I call the method of sections. And it's called the method of sections because we physically look at one piece or one section of the truss, and we determine that everything acting on that truss also has to follow the rules for static equilibrium. So what I can do is, to find a section, I can just cut through the truss like this. Now that I know my reactions, all I have to do is to take what's going on one side of it and then consider everything that has been cut as being a force. What that will do is get me to the force in DF right away, the force in DE right away, and this is sort of a casualty. They'll have to find this one as well. But what it means is I'm going to have 3 unknowns, and since I have 3 equations, I have confidence that I'm able to solve this section right away. Now, if I'd used method of joints, I would have had to find this and this, then I would have had to come up here and found this and this, then I would have had to come here and I would have had that, I would have found this and this, then I would have had to find that. So in other words, it would have been a lot more complicated. This I can do in like a one-step process. All right, so what I'm going to do, I'm just drawing the piece of the truss that is to the left of my cut. This is point C, this is point D, and then what I have here from D to F is the force in DF. Okay, I also cut here, so this is the force in DE. And here's point C, and I also cut here, so this is the force in CE. So I have CE, DE, and DF. Cut, ready to analyze, and away we go. So what else do we have going on this truss? Well, we have a reaction at C in the y direction, which is pushing up. And I know that value is 50 kips. All right, so that means, kind of wish I'd drawn this truss like this. Okay, so I have one force, two forces, three forces, and I can solve directly. Everything that is to the right of my cut, I can ignore, because this piece of the section, this section of the truss, also has to be in static equilibrium. Now the first thing I want to do is to check the signs of my cut forces. If you notice, this goes down and this goes over to the right. Now these two are purely vertical. This one is horizontal and vertical. So that means that if this force goes to the right, which I really don't know if it does or not, it could go to the right or to the left, but I'll find out in the signs. That means that this one's going to have to go this way because it's the only thing that's opposing it. If this goes to the right, that has to go to the left. That also means that this is down, this is up, and I really don't know if this is up or down, do I? But I'm going to find out in my signs. All right, so now I'm going to do, here are my forces, D sub F, D sub E, C sub E, and R C Y. And I have to break those into components, say the summation of those four things in the x direction have to be 0. Some of them don't have x components. This doesn't have an x component, and this doesn't have an x component. What that means is the entirety of CE minus the component of DF in the x direction have to equal 0. All right, and then in the y direction, this has a y, this is purely y, and it's positive RCY minus DE. This is purely horizontal, so it doesn't have a component, but in the y direction, this is down minus the piece of DF in the y direction. Those three things have to equal 0. Now, if you notice, I have 3 unknowns and only 2 equations. That means I have to do a moment equation in order to finish this job. And on this section, I can choose any point and take the moments about that point, and they also have to sum to 0. So if I look at my truss, if I choose point D as a point I'm going to take moment about, I'm only going to have this force and this force that are going to be creating moments about point D. So that's going to simplify my work pretty quickly. So I'm going to say the moments about point D equals 0. I have the moment from CE about point D. And if I put a pin here, CE is going to spin it counterclockwise, so that's positive. What is the distance, the vertical distance from C to D? No, excuse me, the horizontal distance from C to D. Well, on the original drawing, C is here, D is here, the panels are 6 feet, so that's 6 feet. Oops, can't see that. So the horizontal distance, vertical force, horizontal distance, positive moment. Okay, the other one is C. I'm sorry, this should be the reaction at C. All right, so if I put that pin, that's going to spin it that way. So then the other one, CE, is going to be that positive spin, that counterclockwise spin. But now we need to have the distance between C and D. Since this is horizontal, we need the vertical distance. So if we look at problem 651, from C to D, what is that vertical distance? Well, we're going to have to do a little bit of trig to find out what that is, don't we? So in other words, we need to know this length right here, DE. Okay, so if I do a little DE, looks like this. A looks like this. This distance from A to E in the horizontal direction is 12 feet. And now we can find this angle and then solve for the distance DE. All right, how can we solve for this angle? Well, if you look at the original picture, from A to F, we have all the data we need. We know that the vertical distance is 7.5, and we know that the horizontal distance is 6 times 3. So 6 times 3 is 18, and the rise is 7.5 feet on that larger triangle. So that means the theta is equal to the inverse tangent of 7.5 over 18, or this angle theta is equal to 7.5 divided by 18. Take the inverse tangent of that value, and that angle is 22.62 degrees. All right, so if we have that angle of 22.62 degrees, what that means for us is going to be the same when I'm finding this vertical distance. So I know that the horizontal distance is 12, and if I need this midsection vertical distance, but I know the angle, I have the adjacent and I'm looking for opposite. So I know that opposite over adjacent is the tangent of theta. The opposite is the length of DE, which I'm looking for, divided by the 12 feet, which is the adjacent, and the angle is 22.62 degrees. So I can say that that distance DE is 12 feet times the tangent of 22.62 degrees. All right. So 22.62 degrees, tangent is at 4.4167, and if I multiply that by 12 feet, my vertical distance is exactly 5 feet. So DE, the vertical distance, is 5 feet. All right, so getting back to my moment equation, I have R sub C times the horizontal distance of 6 feet plus CE times that vertical distance of 5 feet. Those are the only two moments on the section. That means that I can solve directly for CE because I have the value of RC, which I calculated to be 50 kips. So it's 50 times 6, negative, plus CE times 5 equals 0. I can solve for that force in CE then. It's going to be 50 times 6 divided by 5, which is 10 times 6, or 60 kips. All right, so right here, CE turns out to be 60 kips. And it appears that my direction is correct. And also, once again, if you think about it, it is pulling on the joint. So CE is 60 kips in tension. All right, now that I know CE, I can go back to some of my other equations, like right here. Since I know that CE, and the way it's drawn is positive, 60 kips, minus the component of DF in the x direction. Well, once again, if this angle is 22 point whatever, this is 22 point whatever. So in trig talk, it's going to be df times the cosine of 22.62 degrees. Those things equal to 0, and I can solve for d sub f. D sub f then is 60 over the cosine of 22.62 degrees. So df, the value is 60 divided by the cosine of 22.62 degrees, and that value then is 65 kips. All right, so the next thing we need to do, we see that d sub f is pushing on the joint. That means df is 65 kips, but since it's pushing on the joint, it's in compression. All right, so in this particular truss, we wanted DF, and then we also want DE. So I can see then that I can solve for DE as a purely vertical force by using this equation. So I can see R sub CY, which is 50 kips, minus D sub E, which is 60. Oh, D sub E is my unknown, I apologize. D sub E, which is purely vertical, and then minus D sub F in the y direction, which is 65. This times the sine of that angle, 22.62 degrees. Those three things added together equal 0. So I can say that 50 minus 65 times the sine of 22.62, bring my D sub E over to the other side, and it becomes positive over here, is equal to D sub E. So if I take the sine of 22.62 degrees, multiply that by 65, this value is a negative 25, or is a positive 25. So 50 minus 25 is 25 kips. Now the fact that it did not turn out negative means that I've drawn it correctly here. If this value was negative, it would mean that the sign was actually reversed. So DE has a value of 25 kips. And since I now know that my problem is drawn correctly, D sub E is pulling on the joint, so that's in tension. All right. So basically what we've learned today are two ways to solve the same type of problem: the method of sections, the method of joints. The method of section can simplify your work tremendously if you're looking for the load on a structural member near the middle of a truss. So you don't have to chase it. You can just go straight to the problem, cut it, look at it as a force, and solve it. And the other advantage of the method of sections is, of course, that you have three equations because you can do a summation of moments about any point on that section. With the method of joints, since you're looking at a joint, the moment equation becomes trivial. And so all you have is summation of x, summation forces x, summation forces y. So those are two ways to do the same kind of problems. So ladies and gentlemen, that is the last lecture over Chapter 6. On your Moodle page, I will assign a couple more problems. So here you'll see that the 6.2 and 6.5 were assigned for the method of section, or the method of joints. Tonight I'll assign 2 problems for the method of sections, and then when we return, we will continue with Chapter 7. So have a great day. Talk to you later.